this video, we'll give a second proof that A5 is simple. And the starting point is going to be this exercise that's on the second homework assignment. We showed that if n is at least 3, then an is generated by 3 cycles. All right, so let's describe this second proof. We're going to suppose that n is a proper non-trivial normal subgroup in A5. If n contains a 3-cycle sigma, because n is normal, it is the union of a bunch of conjugacy classes. So that means that n has to contain all the conjugates of sigma. But what are the conjugates of sigma? We saw earlier that all of the 3 cycles in A5 are conjugate to each other. So that means n contains all of the 3 cycles in A5. But by this exercise, once you contain all of the 3 cycles, you contain everything that they generate, which means n has to be all of A5. If you contain a set that generates a group, you are that group. So how does this argument work? All we have to do is show that n contains a 3-cycle, and then that's going to contradict n being a proper non-trivial normal subgroup in A5. All right, so n is not trivial, so it contains something that's not the identity. So let's call that sigma. And what do elements in A5 look like? Well, how do you write them as a product of disjoint cycles? They're either a 3-cycle, a product of 2 transpositions that are disjoint, or a 5-cycle. And we'll just go through these cases one by one and show that starting from any one of these types of permutations, you can show that n has to contain a 3-cycle. So let's start with the first case. If sigma is a permutation whose product of disjoint cycles is, there's some cycle of length 3, then it is a 3-cycle and we don't have to do anything at all. So I'm going to pause and erase, and then I'll show you how starting from sigma being a product of 2 disjoint transpositions or sigma being a 5-cycle, we can force n to contain a 3-cycle either way. Let's finish this proof. We know that we have some element sigma in n that's not the identity. If it's a 3-cycle, we're done. Let's suppose that it's a product of 2 disjoint transpositions, and let's just name those elements the transposition AB and the transposition CD. So if n contains sigma, n is normal, so it contains all the conjugates of sigma. So in particular, it contains the one that is the 3-cycle ABE sigma ABE inverse. So it contains that conjugate, and it also contains sigma, so it contains their product. So now let's just compute what that is. This first permutation in the parentheses is the transposition BE times the transposition CD. You can check that. And then times sigma, which is AB times CD. And now disjoint cycles commute, so you can switch the order here and cancel out the CDs, and you get BE times AB, which is the 3-cycle AEB. So now n has to contain a 3-cycle, and we're done. So the last case is really similar. Let's suppose sigma is a 5-cycle. Let's call the elements A, B, C, D, E. N contains all the conjugates of sigma, so it contains ABC, sigma, ABC inverse. And it also contains sigma inverse, so it contains the product. And you can check that this first permutation inside here is ADEBC, and then the inverse of sigma is AEDCB, and that the product is the 3-cycle ABD. Okay, so there's some computation that goes into this last part here, but the idea is n has to be a union of conjugacy classes, and then you can show that if n contains one 3-cycle, it contains all of them, they generate an, so that's it. So now we know that n contains something, and if we can show that n containing any particular element and all of its conjugates, and then like sigma, sigma inverse, things like that, force n to contain one 3-cycle, then we're done. So this argument is going to generalize well from A5 up to AN, but the details are going to be a little different in style. So at the first thing that we'll do in the next lecture is use this type of idea to show that AN is simple for any n that's at least 5.